My name is Johan Segers and I will be presenting joint work with John Eenmaal on empirical tail copulas for functional data. Our work is available on the archive. We would like to thank the organizers of the Bernoulli IMS One World Symposium for giving us the opportunity to present our work. In our project, we consider extremes of a random field Xi, which is defined on a compact metric space T, which has continuous trajectories. The question we ask ourselves is, how can we estimate non-parametrically tail dependence functions related to such a random field given an independent and identically distributed random sample of such random fields? To do so, let us consider a finite dimensional distribution at a vector of d coordinates t1 up to td. And tail dependence for such a random vector is characterized by the tail copula. So we propose to estimate this tail copula by the well-known empirical tail copula, which is a rank-based estimator. Then the aim in our work is to prove a functional central limit theorem for this empirical tail copula uniformly over all vectors of locations t, and this up to a certain dimension d. Once such a result is available, then it can be used to do statistical inference on tail dependence for such a random field, for instance to test spatial stationarity or to perform parametric inference on tail dependence. So what is a tail copula? Recall the setup. We have a compact metric space. We consider random continuous functions on such a space T. For each t, we have a random variable Xi of t. It has a distribution function f of t, and we assume that all those distribution functions are continuous, meaning that each random variable Xi t does not have any atoms. Then we can apply the probability integral transform, giving us u of t, which is a standard uniform 0,1 random variable. Now the tail copula is concerned with a joint probability that at different locations the process Xi is large. When transformed to u of t, this is equivalent to the probability that at different locations the process u of t is small. So for instance, given two locations t1, t2, we're interested in the joint probability that u of t1 is less than h of x1 and u of t2 is less than h of x2. This probability is small and needs to be normalized. If the limit exists, then it is called the tail copula. In the paper, we work out these tail copulas for particular well-known families of random fields. The empirical tail copula now arises if, given a sample, an independent random sample Xi1, Xi(n), we replace the unknown marginal distribution functions by their empirical counterparts. And then if we replace the threshold h by k over n, where k is an intermediate sequence. If you perform the math, then what you get is the empirical tail copula. So that's an empirical probability, and it essentially consists of counting trajectories such that at a vector of locations, the ranks are large. For instance, in the picture we have three locations, t1, t2, t3, and at each location, those trajectories are marked which are among the two largest. And so depending on which subvector of locations you take, you will get different outcomes for the empirical tail copula. Centering the empirical tail copula by the true tail copula and multiplying by the effective sample size square root k gives the empirical tail copula process. Now, because of this intermediate sequence, it's actually more convenient to center not by the tail copula itself, but rather by the function that converges to it, and that's the function in orange, and we refer to the corresponding process as the penultimate empirical tail-coupler process. The right way of centering is open for debate. It depends on how you intend to use the empirical tail copula. And if you want to, you could apply a bias reduction, as has been done in the literature. So for the finite dimensional case, the asymptotic distribution of the penultimate empirical tail coupler process is well known. It looks like the one for the empirical coupler process, and notably the partial derivatives of the tail coupler arise through the use of the empirical distribution functions for the margins. Now in the functional setup, an additional complexity arises because if two locations are nearby, tail dependence will be strong and the tail coupler will fail to be differentiable. In order to find the asymptotic distribution of the tail empirical coupler process, we first need to find those of the tail empirical process, so where the margins are supposed to be known. So this is the process W, but without a hat, so with known margins. We consider this process on a domain V, which consists of vector of locations T and vectors of arguments X of dimension D, little d from 1 up to large D. We show weak convergence of this empirical process in the space of bounded of bounded stochastic processes, not necessarily continuous, bounded stochastic processes on V. To this end, we need to control or prove asymptotic tightness, and this means we need to control the oscillations of each individual trajectory. This works by a condition that says that given a fixed location S, you can find small enough neighborhoods such that if on the neighborhood the trajectory u of t is less than a small threshold h, then with large probability it will also be smaller than a slightly larger threshold in dark blue in the picture. Under this condition, the empirical tail process converges to a limit, which is a tight-centered Gaussian process, which has remarkably as covariance function exactly the tail copula itself. For the penultimate version then, for the penultimate empirical tail coupler process, where the margins are being estimated, we work on a slightly modified domain, excluding coordinates, excluding vectors of coordinates where locations are the same. So we only look at vectors of locations that are all distinct. And then we impose a condition, essentially saying that the partial derivatives of the tail copula exist. In the condition also appears an intrinsic semi-metric underlying compact metric space T, a semi-metric which is linked exactly to the tail dependence in the underlying process Xi. And so if the oscillation condition and the smoothness condition hold, if additionally certain bias condition holds, meaning that we can somehow approximate the penultimate tail copula by the actual tail copula at appropriate rate, then we find an asymptotic expansion of the tail empirical copula process in terms of the tail empirical process and then the partial derivatives. So the technical challenge we needed to overcome was, as explained before, is that if locations are nearby, tail dependence is very strong and the uniform differentiability needed to apply the delta method fails. And the workaround that we find was to group locations in clusters of approximately nearby locations, and then within the cluster replace the partial derivatives by appropriate directional derivatives. So in the picture, T2, T3 would be considered as a cluster. In conclusion, we have studied tail copulas and empirical tail copulas for continuous random fields on compact domains. We showed a functional central limit theorem for the rank-based empirical tail copula which works uniformly in vectors of coordinates, and the proof was non-standard due to the lack of differentiability issue, which is specific to the spatial case. I thank you for your attention.